Questions?
When is it all over?
Did you go over test corrections?
Yep.
I don't. When did you do it? Because I don't think I was here that.
Sort of the logistics of test corrections?
Yeah.
The logistics are that, I guess I handed them back on Wednesday? Thursday. Last Wednesday. So 2 weeks from then, is sort of what I want you to sort of have in mind of when the test corrections are due. So that would be, I guess, a week from tomorrow. If the test corrections are, if you're still planning to do test corrections, but they're not ready next Wednesday, then just let me know. And let me know when I'm gonna see them. I don't want them hanging on, I want them off your plate, primarily. So there's nothing special about the 2-week deadline other than I don't want you waiting until the end of the semester. The main purpose and point of test corrections is the ideal is another chance to learn the material. So you're trying to show that you understand what's going on. So test corrections on separate paper. And I think the general rules, separate paper, hand in the original test along with it, with the corrections. Don't use red ink. And if you just put down an answer, you'll get no credit. You need to basically show you know what you're talking about.
Didn't you say that, you would let us know today if we could print off the blank paper?
Yeah, I will let you know at the end.
Okay.
Did you sign when Master Set 8 was gonna be due?
I have not, but yeah, it slipped my mind but I was reminded earlier that I forgot to do it.
Could I request if you do Tuesday instead of Thursday?
Master set 8,
Yeah.
due next, a week from today?
Yeah.
Sure.
So are you still having Master Set 7 today?
I will not grade it before Thursday, so get it in Thursday, it's fine.
Thank you.
Sure. Anything else?
I mean, that includes, did you say get it on Thursday or before Thursday? So could we turn it in on Thursday?
Yes, yes. Be right back. It's still running. Other questions? I think it's running.
Could we work through a question on one of the practice tests or previous tests?
Yeah.
Number 5, it's like car on track.
Okay. So the first two, the road is flat, and the third one is banked. Okay, so the car is going this way, it's going to take the turn. If we did a force diagram, sort of a back-end view, basically that's what you would see right there. What are the forces acting on the car? Go through the exact same process as we've done on all the other Newton's laws problems.
So, normal force up on the car, down on the car. And then weight down on the car and up on the ground. And is that the back or the side view of the car?
That's the back, this is the back end. That's the eyeballs. Looking at that end.
So friction is to the right on the car and the left on the ground?
Yes. There's gotta be something that's pointing, something that's pointing towards the center of the circle. Because otherwise, if there's no force towards the center of the circle, that car's just gonna go straight. All right, so force diagram done. What is the direction of acceleration, assuming it's traveling at some constant speed? Direction of acceleration?
To the middle of the circle?
Yeah. This is a centripetal motion problem, so my acceleration is gonna be in that direction right there. So we set up our coordinate system. I know that one of the axes probably should be towards the center of the circle. And the other one perpendicular to that. Up or down?
But isn't friction supposed to oppose acceleration on the car?
It opposes the desired relative motion. Because the car wants to go this way, that's the desired motion. The friction opposes that.
So why is friction to the right then, if it wants to go forward?
All right, so because I know, so I guess two approaches. One, I know that the net force has to be equal to mass times acceleration. They have to be in the same direction. The acceleration based upon change in direction is towards the center of the circle. So since that is towards the center of the circle, that also has to be towards the center of the circle. There's no other forces involved here. If we put down our checklist, we already took those two into account. There's no hand of God here. There's no rope. That just leaves you with friction. Friction has to be the force that's towards the center of the circle. Since it wants to go straight that way, but the car is going to be going that way, there has to be something that's pulling it towards the arc.
Okay.
That work for you?
Yeah.
Okay. Do we need to break anything up? All right, so equations of motion. How many equations of motion are there going to be?
2.
Yep. It's okay if other people play along too. My equations of motion, well, based upon F equals ma. We'll have an I hat, J hat. What is one of the equations of motion?
J is normal force minus weight, which is mass times 0.
And the other one?
Friction equals mass times acceleration.
And it's centripetal acceleration, so I'll put a little subscript there. Substitution, we have an independent equation for weight, centripetal acceleration, and friction. So we make those substitutions. Which friction's involved here?
Stat.
Yeah, it is static, because we don't want the car skidding at all, so it is static. And as with most of these problems, we look at the maximum value. That's going to be equal to mass times v squared over r. Y is equal to mg. So once we plug that in there, we've got, I think, basically the equation we need for the first two problems. Plug that in. We got mu s mg is equal to mv squared over r. Fortunately, the mass cancels out, so I don't think I gave you the mass of the problem, so you don't need it though. So the first problem was, how fast does he need to go?
Yeah, what's the maximum speed you can go without skidding?
All right, so solve for v, and that becomes the square root of us gr. And that, which is the square root of 0.9 times 9.8 times, I think, 100. And it comes out to somewhere around 30 meters a second. We're about to get a real number.
29.70.
All right. Which is roughly 63 miles an hour. And the second part was how, what's the radius given a certain,
If he's going 30 meters per second, what is the minimum radius of curvature you can take and not skid?
okay. So it should come out to something very similar to 100, but be slightly different. This time you're solving for r. R is equal to v squared over musg. So that's 30 squared over 0.9 times 9.8. Which is something, 103. Say it again?
102.04.
In retrospect, I probably should have. Since that came out to around 30 meters per second, I probably should not have picked 30 meters per second for part B. Oh well. That's what happens when I poorly proofread. All right, so that's A and B. And then part C is if the road is banked. Now, usually every time I put a banked question on a test, somebody comes up and asks, what does that mean? A banked road is a road that's at an angle. As you drive around like this, there's one side is higher than the other side.
We're going off-road.
Or the corners of a racetrack. So in that case, if we have this car that's going around a curve like that, if this is banked, then this is the back end view. And very similar to what we did before, what are the forces acting on the vehicle now?
Normal force
Going
into the road. And then same direction, or not same direction, but like same angle into the car.
what are the forces?
Weight down.
Put it up on the ground.
If the road were banked, would the minimum radius of curvature increase or decrease? So Did I make it frictionless? I don't know if I did.
No, you didn't.
So there's friction involved. Which way is friction acting on it?
Down the ramp, right? Or down the curve?
It would be down the curve. Because if we're looking for a minimum radius, that means that the smallest radius where we're not going to basically go skidding off the road. So we now have friction there, which is keeping you from sliding up the, basically up the ramp. If you went that way, you'd be going up the ramp. What is the direction of the centripetal acceleration?
It's directly to the right.
So what's applying the, over there, the friction was the centripetal force. What's the centripetal force here?
Either the cosine or the sine of friction and normal force.
Yeah. It's part of the normal force and part of the friction are supplying the centripetal force now. So if this angle here is theta, the friction is acting down the ramp, then if we broke that up, this would be the friction times the sine of theta, and this is friction times the cosine of theta. Normal force is perpendicular to that. So if the horizontal is cosine for friction, the horizontal will be sine for normal force. So if we did the equations of motion, although it's not necessarily called for there, but if we did the equations of motion, we'd have y sine theta plus friction cosine theta is equal to m v squared over r, and then y cosine theta minus f sine theta minus mg equals 0. Those doing partial substitution. But ultimately, if you have the bank, when we're relying on more than just friction, we have that we would decrease the minimum radius of curvature. You can take a tighter turn.
How do we gather that acceleration is like flatly to the right?
Because for an object traveling at a constant speed that's changing direction, the acceleration is towards the center of the circle. So this car is traveling around in presumably a horizontal circle here. Therefore, the acceleration has to be that way. If you're picturing the acceleration being down the ramp like we started out with in chapter 4, box on ramp, in this context, if the acceleration is that way, that means the car is traveling around like this, which I hope that you're not.
NASCAR.
Was that?
NASCAR.
You still,
Left
I
turn.
don't think there's a lot of up and down, right?
Left turn.
Oh yeah, you do turn, oh yeah. This is like NASCAR, the acceleration is that way. This is, answer your question.
Yeah, but I was just, so if something is if a force is perpendicular to another force, it'll have the opposite sine cosine?
Yes. Yeah. That's why I did friction first, because that was gonna be easier to break up. Other questions?
Is this video gonna be posted today?
It should be.
Master set 7, number 30. I think for 3B, the speed is the same for each of them right before they hit the ground.
Alright, so this is the 3 objects thrown off the cliff at from the same initial height and same initial speed?
Yeah.
Yeah, yes, the speeds at the bottom would be the same.
And then is it gonna be the same while they're falling as well?
When they're at the same height, assuming we're ignoring air resistance, but that's a conservation of energy thing, that, because one was thrown this way, one was thrown this way, and one was thrown this way. Sort of a Wile E. Coyote trajectory there. When they are all, they start out all with the same potential energy and the same kinetic energy. Because once they're in the air, the only force acting on them is the force due to gravity, which is a conservative force, and therefore energy is conserved. So when they're all at that level right here, their speeds would all be the same. And same with any, pick any level, the speeds would be the same all when they are each at that level. Is that sufficient, or do you have follow-up?
That's sufficient.
Okay. Other questions? All right, so, which test was that from?
This is 2019 1B.
Okay, test 1B 2019, all right, order for that. There's another one that's posted without a solution. The spring 2018 test.